On June 23, 2025, a telescope perched on a mountaintop in Chile revealed its first images to the world, and within them sat a genuinely staggering number. In just over 10 hours of test observations, it had already captured millions of galaxies, millions of Milky Way stars, and thousands of asteroids. That wasn't the finished product. That was the equivalent of a single test run, before the telescope had even officially begun its real job. To put that first-day figure into perspective, most professional astronomical surveys consider a single night of confirmed new discoveries a genuine success. Rubin's earliest test observations, gathered before its formal science mission had even begun, already outpaced what many dedicated survey programs managed to accomplish across months or years of continuous operation. Once it did begin, the numbers got stranger still. In its very first week of full operations, this one telescope discovered more than 2,100 brand new asteroids that no human being had ever previously identified, a number that would represent a career's worth of discovery for most traditional observatories, achieved here in a matter of days. It's built around the largest digital camera ever constructed, capable of photographing a patch of sky equivalent to 45 full moons in a single 40-second exposure. And its actual job, the one it's only just started, is to repeat that process every clear night for the next 10 years. This is the Vera Rubin Observatory, and it isn't science fiction exaggerated hype or a headline stretched for a thumbnail. Every figure in this video comes directly from the observatory's own official announcements and the astronomers who built it. This is the story of what this telescope actually is, what it's already found in its first months of operation, and why astronomers describe its ultimate mission as building the first true movie of the entire night sky. A quick note before we get into it. Some of what you'll find floating around online about this telescope leans on invented urgency or fear-based framing that simply doesn't match anything Rubin has actually reported. What follows here is the real story. And honestly, the real numbers don't need any exaggeration to be genuinely remarkable. To understand why this telescope's achievements are worth taking seriously, you first need to understand exactly what makes it fundamentally different from almost every telescope that came before it. The Vera Rubin Observatory is a joint project of the U.S. National Science Foundation and the U.S. Department of Energy's Office of Science, named in honor of astronomer Vera Rubin, whose pioneering measurements of galaxy rotation speeds in the 1970s provided some of the first strong observational evidence for the existence of dark matter. It's a fitting name for a telescope whose own core scientific mission includes directly investigating the same mysterious phenomenon Rubin herself helped bring to the world's attention decades before this observatory existed. The observatory sits atop Cerro Pachon in Chile, a location specifically chosen for its clear, dark skies and stable atmospheric conditions, ideal for exactly this kind of large-scale, long-duration astronomical survey work. Its main mirror measures T-8, 4 meters across, cast notably at the University of Arizona's Richard F. Karras Mirror Lab back in 2007, nearly 2 decades before the observatory's first public images were ever released. That gap between when the mirror was cast and when the finished observatory finally opened reflects just how long-term and painstaking a project of this scale genuinely is. Designing, building, testing, and integrating every component of a facility meant to operate reliably, automatically, night after night. For a full decade of continuous operation takes years of careful engineering, well before a single scientific image is ever captured. But the telescope's true defining feature isn't its mirror size on its own. Plenty of other observatories around the world have comparably large mirrors. What makes Rubin genuinely unique is the combination of that mirror with an extraordinarily wide field of view and the single largest digital camera ever built for astronomy, the LSST camera, capturing images at a resolution of 3,200 megapixels. Each individual exposure, lasting only about 40 seconds, covers an area of sky equivalent to roughly 45 full moons, an almost absurdly large field of view for an instrument with this level of image, sharpness, and depth. That combination, enormous resolution, enormous field of view, and extremely short individual exposure times, is precisely what allows Rubin to do something no previous telescope has ever attempted at this scale. Rather than spending years capturing painstakingly detailed images of a small handful of specific, carefully chosen targets, Rubin is designed to continuously, systematically photograph the entire visible sky, over and over every few nights, for a full decade. As Yusra Al-Sayad, who manages the observatory's image processing algorithms, explained during the June 2025 First Look press conference, Rubin Observatory's defining feature is precisely this opening of the time domain, paired with its enormous field of view. The ability to not just see the universe in extraordinary detail, but to watch it change continuously across an entire decade. The LSST camera itself represents a genuinely singular feat of engineering. roughly the size of a small car and weighing several tons, built specifically to handle the extreme demands of Rubin's survey strategy. Producing a genuinely useful 3,200 megapixel image every 40 seconds, night after night, for 10 consecutive years, required solving engineering challenges that simply hadn't been necessary at this scale before, from precisely cooling the camera's sensors to maintain consistent image quality across thousands of consecutive exposures, to designing data transfer systems capable of moving the sheer volume of information the camera generates fast enough to keep pace with its rapid observing cadence, without ever falling behind or losing data during a single night's run of observations. Let's walk through exactly what Rubin has already accomplished, because the sheer numbers involved are almost difficult to properly hold in your head. Rubin's very first released image, unveiled at the June 23, 2025 First Look event in Washington, D.C., combined 678 separate individual images gathered across just over 7 hours of observing time into a single composite showing the Trifid and Lagoon nebulae, two glowing clouds of star-forming gas and dust located several thousand light-years from Earth. Astronomers specifically chose to combine hundreds of individual exposures this way because stacking that many images together reveals extraordinarily faint details, wisps of gas and dust that would be completely invisible in any single, shorter exposure, while still showcasing the raw resolving power of the telescope's camera and optics working together. The Trifid Nebula itself gets its name from the three distinct lobes of glowing gas visible within it, separated by dark, dense lanes of interstellar dust known as Barnard 85, which intersect near the nebula's center. Alongside it, in the same composite image, sits the Lagoon Nebula, another vast stellar nursery where new stars are actively forming within thick clouds of gas and dust. Both nebulae are popular, frequently photographed targets for astronomers and amateur skywatchers alike, which made them a deliberately chosen, recognizable subject for Rubin's very first public demonstration. A way of showing off the telescope's raw capability using a target astronomers already understood well, making it easier to appreciate exactly how much additional detail Rubin's combination of depth and field of view was able to add. That combined image, astonishingly, represented only a small fraction of the observatory's true capability. According to the observatory's own release materials, that publicly shown first image captured only about 2% of the area visible in the camera's full field of view during that same observation, meaning the actual data gathered was dramatically larger than what most people ever saw in the widely circulated preview image. In a separate release, Rubin's team also unveiled a detailed view of the Virgo cluster, the closest large collection of galaxies to our own Milky Way, showing two prominent spiral galaxies, three merging galaxies, and numerous galaxy groups both near and distant, all captured within a single observational field. Then came the numbers that matter most for understanding Rubin's actual, ongoing scientific mission. According to the observatory's own statement, in just over 10 hours of test observations, well before official science operations had even formally begun, Rubin had already captured millions of galaxies, millions of Milky Way stars, and thousands of asteroids. Once genuine operations began later in 2025, that pace accelerated dramatically. Video documentation released by the observatory showed more than 2,100 entirely new asteroids discovered in Rubin's very first week of operation alone, a figure covering only known solar system objects that had simply never been cataloged by any previous survey before Rubin's cameras happened to capture them. To put that asteroid discovery rate in context, traditional asteroid hunting surveys, painstakingly built up over decades using more conventional telescopes, have collectively cataloged a few million known asteroids across the entire history of astronomy. Rubin's design goal is to eventually double that entire historical catalog within just its first 2 years of full operation, and to ultimately map roughly 90% of near-Earth objects larger than 140 meters across over the course of its full 10-year survey. A specific, congressionally mandated planetary defense goal aimed at identifying potentially hazardous asteroids well before they could ever pose a genuine risk to Earth. It's worth appreciating just how much manual, painstaking effort previous generations of astronomers had to invest to build up the asteroid catalog Rubin is now poised to double in only 2 years. For much of the 20th century, asteroid discovery relied on astronomers manually comparing photographic plates taken on different nights, searching by eye for faint points of light that had shifted position against the fixed background of stars, an extraordinarily labor-intensive process that limited how much of the sky any individual observer could realistically cover. Even after the shift to digital detectors and automated software in more recent decades, most asteroid surveys have still been constrained by smaller fields of view, requiring many more individual pointings, and correspondingly more total observing time, to cover the same amount of sky Rubin can capture in a single 40-second exposure. Rubin's specific combination of an enormous field of view, rapid exposure times, and fully automated detection software effectively compresses what would have taken previous generations of astronomers decades of dedicated, specialized survey work into a task the observatory can now accomplish as a routine, incidental byproduct of its broader nightly operations. Here's where the story moves from "these numbers sound impressive" to "here's exactly how a single instrument manages to produce them." And the answer comes down to a fundamentally different survey philosophy than almost any telescope built before it. Rubin's core scientific program, called the Legacy Survey of Space and Time, or LSST, is designed to systematically photograph the entire accessible southern sky roughly every few nights, continuously, for 10 full years. Rather than choosing a small number of specific targets and studying them in painstaking detail, the traditional approach used by most large telescopes, including space telescopes like Hubble and Webb, Rubin instead prioritizes breadth and repetition, deliberately observing enormous swathes of sky over and over, specifically designed to catch anything that changes, moves, brightens, or dims between one observation and the next. That repeated observation strategy is precisely what makes Rubin uniquely powerful for detecting what astronomers call transient and moving objects, anything in the sky that isn't static. A supernova exploding in a distant galaxy, an asteroid drifting past Earth, a variable star pulsing in brightness, or a previously unknown object suddenly flaring into visibility, all become detectable, specifically because Rubin keeps returning to the same patches of sky again and again, building up a genuine time-lapse record rather than a single static snapshot. According to the observatory's own projections, each individual object within Rubin's survey area will end up being observed more than 800 separate times over the full 10-year mission. An extraordinary depth of repeated coverage that no previous wide-field survey has ever achieved at this scale. Making that volume of data actually useful requires an entirely separate technological achievement. Real-time automated processing and alert systems capable of comparing each new image against previous observations of the same patch of sky, instantly flagging anything that has meaningfully changed. According to the observatory's own materials, dedicated computer facilities process Rubin's data in real time and issue alerts to astronomers worldwide within minutes of any detected change. A genuinely remarkable feat of data engineering, given that the observatory is expected to generate more data in its first year alone than every other optical observatory on Earth has collected combined across the entire history of astronomy. Sifting through that volume of information fast enough to issue meaningful alerts within minutes rather than days or weeks required building entirely new data pipelines specifically capable of handling a genuinely unprecedented scale of incoming astronomical information. To appreciate just how significant that alert system really is, it's worth considering what astronomers expect it to reveal on an ordinary night. Each night the observatory operates, its systems are expected to flag roughly 10 million moving or changing objects, everything from asteroids and comets drifting across the frame, to distant supernovae suddenly brightening, to the fading afterglow of gamma-ray bursts, to subtle variations in light coming from millions of supermassive black holes scattered across the observable universe. No team of human astronomers could possibly review that volume of alerts manually in real time. The entire system depends on automated software capable of distinguishing a genuine, scientifically interesting change from ordinary noise, instrumental artifacts, or already well understood, predictable variability, then routing only the most significant, unexpected findings toward human researchers for closer follow-up. As Sarah Benito, a member of the LSST Discovery Alliance's board of directors, put it, if something in the sky moves or changes at all, Rubin will detect it and distribute that information to the entire world in real time, meaning astronomers everywhere will effectively be able to watch transient astronomical events unfold as they happen, rather than reconstructing them well after the fact from scattered, incomplete observations. It's worth stepping back and asking why an observatory built primarily around breadth and repetition, rather than the deep, narrow focus of instruments like Hubble or Webb, represents such a significant addition to modern astronomy. Because Rubin is specifically designed to tackle scientific questions that simply cannot be answered by staring intently at a small number of individual targets, no matter how sharp or detailed those individual observations might be. One of the observatory's primary scientific goals is investigating dark energy, the mysterious force believed to be driving the accelerating expansion of the universe, and dark matter, the invisible material that Vera Rubin herself helped provide the earliest strong evidence for back in the 1970s. Both phenomena are best studied not through single, isolated observations, but through statistical patterns emerging across enormous numbers of galaxies, tracked consistently over long stretches of time. Exactly the kind of data Rubin's repeated, wide-field survey strategy is uniquely built to generate at a genuinely unprecedented scale. Rubin's approach to studying dark energy and dark matter specifically relies on measuring subtle, widespread patterns across billions of galaxies simultaneously. things like weak gravitational lensing, where the combined mass of matter, including invisible dark matter, subtly distorts the apparent shapes of distant background galaxies, and the large-scale statistical distribution of galaxies and galaxy clusters across enormous volumes of space. Both of these measurement techniques require observing an enormous number of galaxies consistently across a very wide area of sky, precisely the kind of statistical strength that only a survey with Rubin's specific scale and repeated observing cadence can realistically deliver. A handful of exceptionally detailed images of a few dozen galaxies, however sharp, simply couldn't produce the same kind of statistically robust evidence that billions of galaxies, tracked systematically over years, are expected to provide. There's also a very real, immediate practical benefit tied directly to planetary defense. By systematically tracking asteroids and other small solar system bodies as they move and change in brightness across repeated observations, Rubin gives astronomers a dramatically more complete picture of potentially hazardous objects in Earth's cosmic neighborhood than has ever existed before. That data directly supports NASA and other space agencies' efforts to identify and assess objects that could someday pose a genuine impact risk to Earth, giving humanity meaningfully more advance warning time than the incomplete patchwork catalogs assembled by previous, more narrowly focused survey efforts. This particular scientific goal wasn't an incidental side benefit of Rubin's broader design. It's a specific, formally mandated part of the observatory's mission. Congress directed NASA, through the George A. Brown Jr. Near-Earth Object Survey Act, to identify and catalog a significant majority of near-Earth objects larger than 140 meters in diameter, the size threshold generally considered large enough to cause serious regional or global damage in the event of an impact. Rubin's LSST survey is explicitly designed to make major measurable progress toward that congressionally mandated goal, systematically searching the kind of orbital regions, particularly objects with orbits that keep them closer to the sun's glare and therefore historically harder to detect, that previous asteroid hunting efforts have struggled to fully cover. Beyond dark energy and planetary defense specifically, Rubin's design is expected to enable what astronomers describe as a genuinely new category of discovery, entirely new types of variable astronomical objects that scientists don't even know exist yet, simply because no previous survey has ever observed the sky with this combination of depth, breadth, and repetition all at once. Every previous major astronomical survey has, in its own way, revealed unexpected new classes of objects once its unique combination of capabilities was finally brought to bear on the sky. And Rubin's specific combination of capabilities, unprecedented in the history of astronomy, makes many scientists in the field genuinely confident that similarly unexpected discoveries are still waiting to be found within the flood of data the observatory has only just begun generating. It's also worth noting how Rubin fits into the broader landscape of major astronomical facilities currently coming online or already operating. Unlike targeted instruments, such as the James Webb Space Telescope, designed to gather extraordinarily deep, detailed data on individual, carefully chosen objects, or NASA's newly completed Nancy Grace Roman Space Telescope, designed for its own dedicated wide-field surveys from space, Rubin's specific niche is ground-based, continuous, whole-sky monitoring over an entire decade. Rather than competing with these other major instruments, Rubin is expected to work alongside them, flagging interesting transient events and newly discovered objects that other, more specialized telescopes can then follow up on with their own deeper, more targeted observations, a genuinely complementary role within the broader astronomical community's overall observing strategy for the years ahead. So here's where this genuinely stands right now. The Vera Rubin Observatory revealed its first images on June 23, 2025, immediately demonstrating a genuinely unprecedented combination of resolution, field of view, and observing speed. Millions of galaxies and stars and thousands of previously uncatalogued asteroids captured within just over 10 hours of preliminary test observations. Once full science operations began, that pace only accelerated. More than 2,100 new asteroids discovered in the very first week alone, with the observatory's full 10-year legacy survey of space and time only just getting started. Over the coming decade, Rubin is expected to generate a genuinely unprecedented flood of astronomical data, more in its first year alone than every other optical observatory on Earth has produced across the entire history of the field combined, systematically rephotographing the same patches of sky more than 800 times each, specifically designed to catch supernovae, asteroids, variable stars, and entirely new categories of cosmic phenomena nobody has ever previously observed or even properly theorized about. It's worth remembering that everything described in this video represents only the very beginning of Rubin's planned operational life. The observatory's first images and its first week of asteroid discoveries happened within the earliest stretch of a mission designed to run for a full decade. If the discovery rate demonstrated in just those first days and weeks continues anywhere close to its current pace, projected forward across the entire 10-year survey, the cumulative scientific output by the time Rubin's mission finally concludes could genuinely reshape entire fields of astronomy, from the senses of small bodies in our own solar system, to the fundamental physics underlying the universe's accelerating expansion, to categories of transient cosmic events that, as of today, in mid-2026, haven't even been named yet. The real question isn't whether there are still genuine discoveries waiting in the night sky. Rubin's very first week of operation already proved there clearly are, cataloging more new asteroids in 7 days than most entire research careers managed to find. The real question is, what else is waiting in the 9 years and 11 months of observing time still ahead of this telescope? And how many of the strangest, most genuinely unexpected discoveries in modern astronomy are about to come from a single mountaintop observatory in Chile? Simply because, for the first time, humanity finally built an instrument capable of watching the entire sky change in real time. If you want to be here for every new discovery Rubin makes over the course of its 10-year survey, subscribe to the channel and turn on notifications. Because as that data keeps coming in, we'll break it down here with the real numbers, not the invented version. 1 telescope, 1 decade. An entire sky finally being watched all at once. That's a genuinely remarkable achievement on its own terms, without needing any invented drama to make it worth paying attention to. A mountaintop observatory in Chile, quietly generating more data in its first year than the entire prior history of optical astronomy combined, simply by doing the patient, systematic work of watching the same sky over and over for 10 straight years. Thanks for watching.